Welcome, this is lecture number 35. In this lecture, we are going to talk about design of voltage mode control buck converter, and the design is primarily intended to shape the loop for closed loop performance as well as the output impedance. Okay. So, in this we are talking about type 3 compensator design in a voltage mode control, then identifying loop shaping objective, then robust compensation within admissible control bandwidth, then design method for shaping output impedance. So, loop gain analysis of a buck converter. This loop structure we have already seen in the previous lecture. So, I am not going to spend time on it, and the control to output transfer function, that means this particular transfer function that we know, it is here, okay, where alpha we have discussed R plus R equivalent, that is the total resistance DCR plus RDS on ESR 0, then this is the LC filter pole, and this can be approximated to be 1 by square root of LC, because if RE and RC are close to each other, or particularly if the load resistance is higher than RE and RC, which is the case. Now, one thing we will keep in mind, this is a Q factor which consists of parasitic, that means ESR, R equivalent, characteristic impedance, where the characteristic impedance is nothing but square root of L by C, but this is the one which can affect the QC. That means, and this you can see, if you compare these two terms, this term will be negligible when R is very large or light load condition, okay, and under high load condition when the R is small, then this will be dominating, like R ZC by R will be a dominating factor. Okay, so, we have to keep in mind for practical compensation point of view. Next, our primary loop shaping objective. So, here our primary loop shaping, we have to cancel, we are planning to cancel ESR 0. So, we need to consider, that means we need to have a one pole of the controller to cancel the ESR 0. We need to cancel double pole to offset the sharp fall, right, due to the double pole. In fact, this is the one which we will consider when we talk about robust compensation, because the double pole may not be perfectly known because of variation in the load resistance, but we still need two zeros to compensate that, controller zeros. Okay. We need to consider one integrator in the controller which will try to eliminate the steady state error, or it will provide sufficient DC gain. So, we need one more pole in the controller. Okay. We also need to consider another simple pole, because in the previous lecture we saw another extra pole will give another degree of freedom, okay, which was not available in the PID controller. So, we could not shape the transient response under wide operating range, and now we have it because in type 3 compensator. So, one more pole, and then we need to set the gain of the controller to achieve desired gain crossover frequency. So, we can that means we need 3 poles and 2 0, and this is nothing but type 3 compensator, and PID controller may be enough for ideal buck, but for practical buck we need a type 3 compensator. The another point, here we can independently control, we will see both crossover frequency as well as the phase margin. Okay. So, type 3 compensator characteristics we have discussed, it has 2 zeros and one pole at origin and other 2 poles, okay, and this is the controller DC gain, sorry, not DC gain, that is a controller gain, and first it has an integrator, then there are 2 zeros, right, and 2 poles, and we will want to see how are you going to place those poles and zeros. So, it has one extra pole compared to PID controller, and that is why it gives another degree of freedom, and we can measure the phase response, phase margin, and we will see that 2 degree of freedom will be given, one crossover frequency and phase margin, which is not there because PID controller has 1 degree of freedom, because it always analytically shows 90 degree phase margin, but practically we saw that model is not accurate enough even for a low control bandwidth. Now, the perfect compensation, if you take the loop transfer function, then the controller is a type 3 compensator where it has a numerator 20 and which is like your 0 of the controller is designed to compensate the denominator of this plan. So, we are doing pole 0 cancellation, and one of the pole is used to cancel the ESR 0. So, this is what exactly I told here, we are trying to cancel. The second one, the first pole we are using the ESR 0, and since we have an additional pole of the controller, so which is taken as a WP omega p, and we have to find out where to place the additional pole, that we will discuss. But that means the controller has 2 0 is used to cancel the double pole, but we will talk about the robust compensation, and controller has 1 0, one pole is used to cancel ESR 0, another pole is the flexible pole. Okay. Next, now if we substitute S equal to j omega, because we want to do frequency response carry out, then these terms along with the controller Kc, that means the loop transfer function will look like this, right. So, this is a loop transfer function after cancellation. This is a simple pole of the controller which we want to place, and here we can consider another p and we can multiply it with p, because we want to write in the form of S by WP controller pole. Okay, that exactly we did here, right. So, we took this, that means, and we took this. Now, we substitute S equal to j omega. Our next task, we want to replace this omega by omega p is equal to omega n. It is something like a used for normalization, because it is a ratio of two frequency, where omega is the instantaneous frequency related to the frequency response, and omega p is the pole of the simple pole of the controller which we want to place. So, the normalized loop gain will take the form KL into this, where KL, what is KL that we have discussed? KL is nothing but, wait, so we want to write what is KL? KL is nothing but Fm V in Kc by alpha omega p. So, you should keep this in mind, okay, and this is a normalized frequency. Now, yeah, this is what we have already written. Now, consider loop gain in polar form. So, this is in the Cartesian form, and we need to convert into polar form, because we have two complex number, this one and this one, two complex number. So, you can treat like this is x and y, right. So, there are two complex number. So, in the polar form, we want to write in terms of amplitude and angle, right, magnitude and angle. So, what is the magnitude? If you take this polar form, KL is already in terms of magnitude, okay. So, there is no, it is a real number, right, and it is of course a positive quantity. Then for this term x, that means this term, your magnitude is simply 1 by omega n, and for this term your magnitude is simply 1 by 1 plus omega n, the square root of 1 by omega. So, this is the overall magnitude of this. Then what is the phase? You see, the phase due to this is nothing but minus 90 degree, because it is a 1 by s term, 1 by j omega, right. So, it is a complex number minus 90 degree, and the phase due to this term, that means if you use a different color, the phase due to this, the theta contribution this, theta is nothing but this quantity minus of this, and minus 90 degree is coming due to 1 by j omega n, it is coming due to this, okay. And the in polar form, the phase, if they are product, then the phase can be added. If the two complex number, if you do the product of two complex number, the phase will be the sum of their individual complex number phase of the, okay. So, at gain crossover frequency, our magnitude is 1, because in polar form we have a magnitude which is a function of omega, and it is nothing but, what is omega n? Omega n is nothing but omega by omega p, where it is the instantaneous frequency and it is the pole frequency, that is our controller pole. Now, at gain crossover frequency, that means what is this? It is nothing but R of omega c by omega p, right? That is equal to 1. And what is this? That means this, if you go back, what is R? R equal to this. That means at gain crossover frequency, this quantity is 1. Okay, that means this whole quantity will be 1, which is computed at omega n is equal to omega c by omega p, that is a gain crossover frequency. Then this quantity will become unity. Okay, this is exactly what we did, and from there we can write this omega n is nothing but omega c by omega p, and there was another term here. So, this ratio, so square root of this. So, this is a very important relationship. Okay. Next, that means we got one relationship. Next, phase margin. So, at gain crossover frequency, our phase margin can be computed 180 degree plus the phase contributed by this, which is the theta of this. This is a phase contribution. We are talking about the phase contribution. Okay. And this can be written as 90 degree minus tan inverse of omega c by omega p. From here, from this relationship, we can write omega c by omega p is nothing but phase 90 degree minus phase margin. Hold on. So, you can simply write it as a 90 degree minus phase margin, this whole thing tan of this. Okay. So, here if we decide omega c, then we can find out omega p. Okay. That means we can find out omega p as a function of omega c from this relationship. Okay. That means we can now, if we set the crossover frequency, then we can calculate Fp for a given phase margin, if the phase margin is given. That means two things you have to keep in mind. First, we have to decide, that means decide your phase margin, Pm, okay, sorry, phase margin. Then number 1, then decide gain crossover frequency, or you can say omega c in radian per second, right. If you decide phase margin, then you will get a relationship between Fp and omega c, and if you set omega c, then you can find out omega p from this relationship. So, that means you can get these two value for a given phase margin as well as for a given cutoff frequency. That means calculate the controller pole, it can be computed from this relationship. That means if you provide the phase margin, then you can relate omega p in terms of omega c, and if you provide omega c, then you can compute the controller gain, because it is coming from that K relationship, right. So, it is coming from this relationship. Okay. So, now what happen if we set the controller port at the crossover frequency, then it can be found from this R omega n, it is equal to 1. Since we are setting omega p equal to omega c, so omega n is equal to 1, where omega to omega c, crossover frequency in this case. So, this is also 1, this is 2. So, we will get Kc will be alpha omega c Fm into square root of 2, because of this term will be square root of 2, 1 plus 1 square root. Okay. And if you find out the phase margin, first of all angle will be omega n is 1. So, it is 45 degree. So, here it is minus, this is 45 degree, this contribution, and if you calculate phase margin, it will be 45 degree. Okay. So, more, that means now we have to go to MATLAB simulation and to check. So, now we are asking for, so this is the expression that we have derived, all the transfer functions are given, numerator, denominator, controller gain. Now, we are designing the compensator. That means it will ask for cutoff frequency or crossover frequency and will ask for phase margin. That means there are two possibilities, right? And suppose you want to do 0.1, suppose you want to design we want to do closed loop transient performance, and we set the controller bandwidth to be like you select it. So, we will see how far the model is valid, then phase margin as per our wish, then we can compute analytically all the value that we have and here we are talking about exact pole 0 cancellation. So, numerator of the controller is nothing but Kc into the denominator of the plant, which is the power converter poles, this is the poles, okay. And then the denominator of the controller is nothing but that there are two zeros, two poles are there, one and also three poles, one at origin and one to cancel ESR, another is the flexible controller pole which we got from the analytically, right. So, let us design and check the MATLAB simulation. So, suppose we want to select the bandwidth, that means bandwidth same as, so that means let us set first. So, there are two things here. If we set the bandwidth, let us say 50 kilohertz, it is in kilohertz, 50 kilohertz, our switching frequency is 500 kilohertz. So, that means your crossover frequency is showing 50 kilohertz and phase margin, just 1 minute, phase margin if we set let us say 45 degree, because we know if the crossover frequency is 50 kilohertz and if you set the phase margin 45 degree, then you should get the controller pole at the same location, right, that you have learned, okay. So, that means gain crossover frequency is 50 kilohertz, phase margin is 45 degree. Now, we want to see what is my controller pole, because let me find out what is my omega c. So, this is in radian per second crossover frequency, what is my controller pole? So, they are exactly equal, it is coming from the mathematical expression here omega Cp, and what is kx here? The ratio of the two, k of x is equal to 1, because we have learned that from this expression that this kx, which is a normalized frequency I took, is equal to 1 when if it is set to same, they are same, then it will give it to 45 degree phase margin. That means, we are checking the other way, we are setting 45 degree phase margin and we can see that omega n is coming to be 1. So, which is consistent, okay, right. So, now we obtain 45 degree phase margin and this is the response of the converter coming from the and if we check the Bode plot, okay. So, let us use a different okay. So, let us once more, because green color may not look good. So, Bode plot, okay. So, again we are running 50 kilohertz and 45 degree phase margin, okay. Now, Bode plot, if you look at the Bode plot and if you want to plot all the, so it is in radian per second. So, you have to convert into hertz first. So, it is in hertz now, and we can we want to find out what are the stability margin. So, you see we are getting 50 kilohertz crossover frequency, 45 degree phase margin. So, it is perfectly consistent with our given specification, and this is a response, that means this is the reference transient performance. I mean, it has a high overshoot, like around 20% overshoot, but we need to check whether the response matches with the our converter response or not, that we want to check, okay. Okay. So, it looks like they are not matching quite accurately, because even we have set 1/10 bandwidth, but it is not perfectly matching, okay. So, I think we should use a different color here, okay. So, that means they are not matching perfectly. So, if we hold on, grid on and again re-evaluate, okay. So, if we set that the response obtained from the small signal model is not exactly matching with the response obtained from actual switch simulation. So, they are deviating, that means the model is not perfectly valid. Okay. But if we reduce the cutoff frequency, suppose if we redesign the one, if we reduce to, let us say we make earlier it was 1/10, now if we make like a 1/20th, let us say we are making 25 kilohertz and 45 degree phase margin. This is a response which we obtain from so now we want to obtain from this. Okay, so it looks like now the second case they are matching somewhat reasonably. So, let us plot once more, because we have okay. So, we have we are setting 25 kilohertz, 45 degree phase margin, and this is a response, and if we do actual switch simulation, so they are matching somewhat reasonably accurate and not exactly matching, but yeah, with reason. So, in this case the at least the validity is coming to be 1/20th of the switching frequency, because maybe the step size is large. That is why, because it will be clear from the current waveform, the reason is nothing but the duty ratio perturbation is somewhat larger. So, they are not exactly matching, but closely matching. Okay. Now, we want to design for higher phase margin. Suppose we do 50 kilohertz and provide 60 degree phase margin. Okay. So, now if we run the simulation 60 degree phase margin, so we want to check that how far the response is valid. See, response is not valid, because for maybe the step size is large. So, actual response of the converter is somewhat deviating from the response obtained from the small signal model. Okay. Okay. So, we probably have to reduce the bandwidth, I am sorry, we have to probably so if you go to the parameter file, our ESR is too small. So, if you take a little larger ESR, then hopefully it will, because we need to properly damp. So, now 50 kilohertz with 60 degree phase margin, and if we run it, then I feel that they will match, because it was like close to ideal one, the ESR was too small. So, now it is 1/10 switching frequency is matching. That means, the matching depends on also ESR. For a little larger ESR, you can go a little bit like up to 1/10 switching frequency, you can get reasonably good matching. But if we are reducing ESR, then the validity of the model will even get degraded at 1/10, because even we have to operate at a slot switching frequency. But what I want to mean that it is a well damped response, the closed loop performance. Okay. And if you see the Bode plot, so we can check the Bode plot response. Now, so this is the response that we obtain for, we can do more practical compensation case. So, here we have exactly cancel the poles, but suppose we do not know the exact value of resistance. So, what will happen if you take the QP, that means if you take the QP, because QP is what? Earlier what was the Q, our original Q, that means if you check the, what is the Q expression? If you recall, our original Q was, I think it was RE plus RC by ZC, sorry, plus ZC by R inverse, yes. And I told you this term will become significant when the load resistance is very high, otherwise this will primarily dominate, right. Now, if we design QP at R min, that means at the highest load current condition, then what is it, I mean what is going to happen. Okay. So, let us go back and change our compensator. So, now we are trying to design a more practical, that means we want to get Q max, and Q max is calculated in one case where we are taking R min, minimum value of R, and let us say R min is equal to I 0 max, I mean maximum load current. Okay. So, now we have used that Q max, and instead of using earlier one, so we have the response already plotted. So, now we want to compensate with maximum one, and now we want to change the color. So, it is a now green color, and let us hold it because everything will be erased. So, again we are okay, I 0 max probability is not defined. So, if you write the parameter file, okay, so we have to define what is I 0 max. So, we will define I 0 max is nothing but 20 ampere. Okay. Now, it will ask for 50 kilohertz and 60 degree phase margin. So, this is a response with compensation where we have not included load resistance term. It is based on the lowest value of load resistance, and we will see what happened with the actual converter response, and there we want to use a different color. Let us say we will use maybe the dotted one. Okay. So, we will use a dotted one and see what is the response of the converter. Yes. So, it looks like the response of the converter does not change drastically. This is with the worst case scenario that we are compensating. That means, we are trying to compensate with exact cancellation and with robust compensation, and there if you see their current response, inductor current response, they are also very close. That means, we do not need to know exactly the value of the load resistance, they are quite matching. But now, if we want to extend this when the load is light, that means under 1 ohm condition, we want to redesign it. Okay. So, one case we want to use this robust compensation, we want to now use 25 kilohertz cutoff frequency, 60 degree phase margin, and this is something using robust compensation, and where this is the one with the actual switch simulation. Okay. So, we want to check that how far they are matching. So, they are matching nicely, but there is a much overshoot undershoot response. Now, if we want to do exact cancellation, now we want to keep this one and using red color. So, we are changing the color to red, and we are using here the compensation. Here we are using the denominator C, the exact cancellation. Okay. And we are running it. Again we are using 25 kilohertz and 60 degree bandwidth. Okay. And now we will consider the second one, which is the color. Now, so here we are compensating using, yes. So, here it looks like if we use the maximum value of the load resistance at minimum value of load resistance, it may not be a good solution at light load, because at light load the term, this term is dominated. At light load this is very low, this is dominated by this term. That means, we want to use QP rather RE plus RC by ZC inverse, or basically characteristic impedance RE plus RC. This is a more robust compensation that is used for the controller pole. So, you are not going to, it is not going to cancel this, we are not going to cancel this. And if you do that, then let us see what happened. Now, we want to redesign again. So, maybe we can consider another design case study where, or it will be too much, waveform will be too much. So, here we will set simply, so now Q max we are setting simply that parasitic element, no load resistance dependency term. Okay. So, now this is the one with our 25 kilohertz 60 dB phase margin, and here our actual converter response. This is with exact compensation, exact pole 0 compensation. The second one we want to do with this robust compensation, where our compensator 0 it will be max, okay, where you see the max is set to where is that? Yeah, it is set to Q max. We have just changed this. Okay. Now we want to use green color, and if we can match the response to linear model, then that should be good enough, but we can still check 25 kilohertz 60 degree phase margin. So, this is with robust compensation. Sorry, it has actually eliminated all this waveform. So, this is the robust compensation method. And what we wanted to design, we should have retained this. Okay, so let us retain the whole value, that means so 25 kilohertz 60 degree phase margin. Yes, so they are closely matching, that means exact cancellation and robust compensation, they are closely matching. The yellow, that means your red one is exact cancellation and the green one is a robust compensation. And if we plot this this exact cancellation now using a different color, this is exactly what is going to happen. Yeah, they are closely matching. That means it is recommended to use this compensation technique. Okay. Okay. Next, more practical case study we have discussed. So, QP, it turns out to be, it would be better to use insensitive, that means we can use simply ZC by RE plus RC. But when the load resistance is low, then that means high load condition, it might be problematic, because then that term will get dominated. So, let us see what happened for the condition when load resistance is very low. Okay. So, it is like a 10 ampere you are designing, or maybe you can design for the 20 ampere. So, the first case we are showing with exact cancellation, and this is a response. We are talking about 50 kilohertz 60 dB phase margin, and if we match with this, this is exact cancellation. So, we want to match the response of the system. This is under highest load current condition and the model is matching quite nicely. Now, we want to compensate using conservative approach. Which one? We have selected the Q max to be this value denominator max. So, we will just use this in the compensator rather than, and now we will use a green color and see how does the response look like. So, 50 kilohertz 60 dB phase margin. So, response is not, it is again kind of overcompensated. Okay. So, here probably we need to trade off between So, now if you go back to our converter response, if I draw the dotted line. So, in terms of design point of view, so this is not a bad design, but it is more robust design, where it may have a little longer settling time, but that is fine, but at least it is insensitive to parameter variation. A slightly increase in the overshoot undershoot, otherwise in the average sense they are matching fine, but yes, you can expect a little longer settling time because of this compensation, but it is not significantly high. Okay. So, I think the method using this is, I think is maybe more robust. So, now we have to talk about output impedance. Now, if we talk about output impedance under voltage mode control, this is the open loop output impedance. and the closed loop output impedance can be taken as, this is a DC characteristic, and we have discussed this output impedance in lecture number 13 when we tried to model the actual source. So, now this output impedance of the converter, right. Now, open loop output impedance we have discussed, different poles and 0 already we have discussed. So, now we want to see what is the closed loop output impedance. That means the closed loop output impedance is nothing but the open loop output impedance divided by 1 plus loop transfer function. So far we have used different type of technique. So, suppose if we consider let us say exact cancellation. For example, let us consider exact cancellation. Then we want to see what happened for closed loop output impedance, because so far we have discussed about step transient of the reference voltage. Now we are talking about the output impedance. So here we have the expression of the closed loop output impedance. So we need to plot also the Bode plot of the closed loop output impedance of different the loop transfer function, okay, and then we want to apply, let us say 20 ampere load step transient, and let us set the load resistance to 1 ohm. So we are making a load transient, okay, where now there is no reference transient, and we have discussed that for that we need to, this will be minus of delta load step size, that means this size, okay, and here it should be output impedance, that means ZOC, okay. So let us now try to, so bandwidth let us set 50, 60 degree phase margin, and we will see is a very much oscillatory behavior, okay, is oscillatory behavior, and we want to see what is the response of the system of the actual switch simulation. So we have applied a load step transient, and you see that they are matching quite accurately, that load step transient. That means your actual switch simulation and the small signal model, they are matching, but the response is not very satisfactory. Why? Because if you go back to the Bode plot, so this is a Bode plot, you will see the red one is the loop transfer function, okay, and if you see all the stability characteristics. So we are getting, we have set 60 degree phase margin and it is in radian per second. So we should change it unit to hertz, okay, and then we are setting 50 kilohertz bandwidth. But open loop output impedance, you see at low frequency it is much higher than the closed loop one, and then there is a peaking, and then it is getting this point at high frequency, it will be decided by the ESR that we have discussed. And output impedance at high frequency, your inductor will behave like an open circuit. So it is a RC circuit, capacitor will behave like a short circuit, then RC and R parallel combination will give you the output impedance at very high frequency. And for open loop low frequency, it is RL and R will come in parallel, that we have discussed. But in closed loop we can reduce the low frequency output impedance, so that we can make the converter, that means if it is a voltage source, we are trying to achieve a very low DC output impedance, so that it has almost nearly perfect voltage regulation for the entire load range, for the nominal load range. But at high frequency, that ESR, that effect cannot be avoided, that will create a jump. In order to, but this ringing effect is coming. So what can you do? Because you know the expression, if we increase the loop gain, then this output impedance can be reduced, the effect can be reduced if you increase the loop gain, okay. So now what we are going to do, we want to increase the loop gain. That means here our transient response shows that almost 15% overshoot, undershoot, and also the settling time is quite large, because it takes sort of 0.25 millisecond, which is not fast enough. So then what we have to do, we have to increase the bandwidth. Let us increase the bandwidth. Suppose we want to achieve the bandwidth, let us say instead of 50 kilohertz, 100 kilohertz. though we have to check the model validity, 100 kilohertz bandwidth that we are going to achieve. Now, we run the actual switch simulation and check what happens. So, earlier it was a 15% overshoot undershoot. Now, you will see first of all the model mismatch start coming into picture. So, that means models are not matching nicely, the predicted behavior and the switching behavior are varying, but we could reduce the overshoot undershoot within 10%, right, and we can also increase the settling time nearly. So, it is more or less same, not very much improved, but we can reduce the overshoot undershoot. That means, essentially what we are trying to do by shifting up the loop gain, by increasing the loop gain, because we are trying to increase the crossover frequency, we are trying to reduce this peaking effect, because the closed loop output impedance is the open loop output impedance divided by the 1 plus loop gain, but high loop gain around this peaking frequency can reduce the impact, but this is not a solution because we cannot set the loop gain to be very high. So, what is the alternative solution? So, alternative solution is that we want to shape the loop gain at very light load, R is much larger than this very high resistive load. Then we can simply take the effect of this RD to be equal to RE, okay. This is equal to RE, and the control to output transfer function is GVD, all this we know. So, the closed loop output impedance, if you see the expression of this output impedance and the control to output transfer function, ESR 0 is common, ESR 0 is common and the poles are common, right, common. So, we can write the output impedance in terms of the control to output transfer function into that additional 0, okay, this additional 0, okay. So, now next, so the closed loop output impedance can be written as that the loop gain, this product, and the loop gain can be written like this, and then closed loop output impedance expression, if you write the open loop output impedance divided by 1 plus loop transfer function, and we have already obtained the output impedance in terms of control to output transfer function, and loop gain also have a control to output transfer function. So, if you want to, now this is the expression, the closed loop. So, the closed loop output impedance can be written as open loop divided by 1 plus this loop, here it is the expression T. So, we have now we want to make the closed loop output impedance nearly independent of frequency, that means frequency independent. Is it possible or not? That means, we have to set the resemble like a resistance. If we can do that, then our initial voltage source discussion, if we have just a resistance in series, no infinite bandwidth, that means it can respond to any frequency. Can we do it or not? So, can we make the whole closed loop output impedance to be simply a resistive output impedance, and what should be the value of resistance? So, that is our objective. Now, so we need to make this R and we need to find out what is the value of R. So, first of all, that means this is just this term I am taking this side. So, next expression. Now, there is a constraint. What is the constraint? The resistive closed loop output impedance should be larger than or equal to ESR. Why? Because if you take the output impedance, then it is a parallel combination of RLC. At very high frequency, this will be open circuited, this will be shorted, and that means your RC and R will be in parallel. So, which can be written as roughly RC if RC is very small. So, you cannot achieve output impedance smaller than this, because this is the limiting factor. Okay. So, it has to be smaller than this, and that means now GC, from this expression we need to find out what is GC. Okay. So, GVD is known, everything is known, only GC has to be found in terms of R. Okay. So, now GC is written like this, and if you substitute GVD, so that means this R, that means this is our closed loop output impedance that we want to obtain, and if you substitute this expression into this one, then you will get a numerator polynomial and the denominator polynomial. Okay. Now, Since we want a proper transfer function, so a square term coefficient must be 0, whatever term square. That means, for numerator polynomial, a square term coefficient is related to this. That means, we can separate out the term coefficient associated with the a square is nothing but this term. Okay. So, we want to make this 0 because we want a proper transfer function, because your denominator is a first order system and we need to set to must be 0, and if we do it, then it turns out to be, by substituting this and this will get cancelled and you will get something like, from this equation you will get R equal to R C. That means, I can set the closed loop output impedance look like a resistive ESR, it is the ESR. So, now if you substitute ESR, then you can find out the expression, the numerator and denominator polynomial of the original expression, because we have this original controller transfer function, this is the original expression. So, we have to substitute this R, then these things are known. So, then is substitution, we will find out that controller transfer function, it can be shown that the time constant of the inductor will be larger than than the capacitor time constant, because ESR is much smaller. I am sorry, so it should be RE by, okay, it should be LE, yeah, sorry. Now, here we are getting one expression which is RE by, L by RE, okay. So, yes, I think we are getting a term RC common, it should be fine, it is like it is fine. So, this term, so we can find out that this term should be greater than 0, okay. And because these two are in micro, because what is L? L is our 0.5 micro divided by RC, which is 3 milli, right. So, if we substitute RC equal to 3 milliohm and L equal to 0.5 micro Henry. So, L by RC will be 0.5 by 3, that is 1 by 6, and it will have a dimension of 10 to the power I mean minus 3, right. I will check that, and what will be this? It will be 3 into 10 to the power minus 3 into, we have taken 200 into 10 to the power minus 6. So, we are getting 600 into 10 to the power minus 9. That means, if we write in terms of this one, so this term, that means this is positive, okay. So, this is correct. So, if you now substitute the RD, we have taken approximately equal to RE, then since RE equal greater than RC, because the summation of DCR and the RDS on should be larger than ESR, because you have to take the ESR small, then the transfer function of the controller looks like this. So, this resembles this is a gain. So, this resembles a first order lead compensator, where it can be shown that the 0 will be left side and the pole will be right side. So, now we want to consider a lead compensator than our earlier type 3 compensator. So, we will comment this one and now call a lead compensator, okay, uncomment, and let us run it. So, we have run, and now this is the, if you see the closed loop output impedance, it has no peaking effect, it is very much reduced here and going here, okay. And if you see the response of the converter, so the response will transient performance, load transient performance, it looks like extremely fast load transient performance, very fast, and it responds, but there will be slight steady state error because we have not used any integral action, because we have used a resistive droop. Naturally, the resistive droop will slightly vary the operating point, because it is a droop control, and that we have discussed earlier lecture in droop control. So, it is like a, but it is a voltage mode control. And if you see the inductor current waveform, So, the inductor current waveform look like extremely fast, very fast transient response. So, which means the lag lead compensator will be a very suitable choice for load transient point of view, but you may not get 0 steady state error, but by increasing the gain you can reduce the steady state error, but it can almost behave like a immediate response to the transient, and that we got from the response, like it almost respond immediately, I mean almost very small transient, maybe a 1 cycle or so, yeah, because of this finite slew rate of the inductor and capacitor. Okay. So, with this I summarize type 3 compensator design was discussed, then robust compensation within the admissible control bandwidth was discussed, design method for shaping output impedance was discussed, and then MATLAB case study for design of a voltage mode buck converter was discussed in detail. On different design we have considered MATLAB case study. So, with this I want to finish here. Thank you very much.